Alright, hey everyone. So today we're going to be learning introduction into differentiation. So in the past, mathematicians have had problems with determining the accuracy of their answers. So if we were to observe a ball, and let's say it was falling off a cliff, or let's say we had thrown the ball, it's possible, and it has been possible for thousands of years, to graph a distance versus time graph. So if this was my distance and this was my time, it has been possible to observe a ball and graph an equation and then determine the equation of that graph and find things like its speed, its distance, and its time. Now you guys should know from science, junior science, that if I take the gradient of a distance time graph, I actually get my velocity or speed. Now that is important when we learn about calculus. Now, there becomes an issue when we want to calculate the gradient of a distance time graph. And actually, you see this all of the time in the real world. So if you ever are driving along any highway and you see an average speed camera, well, we know that we can't calculate average speed unless we have two or more points. There's no way that an average speed camera can instantaneously calculate your speed when you go through it because it only measures your time and where you are in your distance. So this is where calculus comes into play. If I wanted to calculate the gradient of this line, well, that would be finding my speed. Well, the only thing I would be able to do, let's say I wanted to calculate the speed at this point. Well, the only thing that we could do was to choose two other points and determine the gradient between those 2 points. And then we could approximate the gradient of this point. But that's actually not going to be too accurate. We know that this gradient of this line is not necessarily the speed at this point. It's close, but it's not necessarily accurate. So what we could do is we could instead choose two closer points and calculate the gradient of that line. Well, we're going to get the gradient or the velocity of the point at the in-between or the average speed in between these 2 points. But we're not necessarily going to get accurately the speed at exactly this point. So what we could do is we could move the 2 points closer together, and we could move them closer together again and closer together again. The closer these 2 points get together, gets more and more accurate to be the gradient at this point in red, or the velocity at that particular point. Let's say that was at time 2 seconds. The closer my 2 points together, the closest we can determine the gradient of a line. Now recall from year 9 and 10 that the gradient of a line m is equal to rise over run. And if I had 2 points, x1 and y1, and x2 and y2, the gradient of my line would be equal to, sorry, that should be y2 down there. The gradient of my line would be y2 minus y1 over x2 minus x1. We know that is our gradient formula. We're going to use this gradient formula to develop what we call the fundamental theorem of calculus. Okay. I'm going to draw an axis, and I'm going to plot some random points along a completely random function. That's going to be my function there. Now, if I wanted to know the gradient of that equation, well, I can't. We can't do that at the moment. We know that we can only find the gradient of straight lines, not curved lines. But what if I wanted to know the gradient at this point here? What would I do? Okay, well, we know that the only way that we can calculate the gradient is using 2 points. So what if we called this point, point x, and its corresponding y point, f of x. So this point in red would be x, comma, f of x. And we need to choose a second point. Let's put it over here. And we're going to call this point x plus h. Now that would mean in between these two lines would be a distance of h. We're going to call this point up here, corresponding y point, f of x plus h. I might do that in a different color. So we're going to call this corresponding y point f of x plus h, which would mean in blue we're going to have the point x plus h, comma, f of x plus h. So we've just chosen 2 points, and we're going to calculate the gradient between those 2 points of a line. So, using our formula, gradient m is equal to y2 minus y1 over x2 minus x1. That is equal to y2 is f of x plus h, so it's going to be f of x plus h, minus y1, which is f of x, over x plus h, x2, minus x, x1, which will give the gradient of that particular line, m, is equal to f of x plus h minus f of x. Those two x's on the bottom will cancel, and we have over h. So we've just discovered that the gradient between any 2 points where the x-coordinates have a distance of h between them has an equation m is equal to f of x plus h minus f of x over h. Now we discussed up here that the closer my 2 points get together, the closer I am to calculating the gradient at exactly a singular point. So the closer that x plus h gets to x, the more accurately I'm going to be able to calculate the gradient at this point here. So what we're saying is the closer h gets to 0, or the smaller h gets, and the more accurate my gradient is going to be because my 2 points are going to be closer together. This is what we call the idea of the limit. So we're going to say the limit as h gets smaller, or h approaches 0, of f of x plus h minus f of x on h. So we said that the limit as h goes to 0, the smaller h gets, the more accurately I'm going to get to my point, is equal to f of x plus h minus f of x on h. Basically what we're saying is, if I have my 2 points, x and x plus h, and I make them infinitely close together, then I'm going to get the exact gradient of my point at that particular point. Now, from junior mathematics, you should know that if I have a circle and I draw a line that touches the circle only once, I call this a tangent. You guys should know that. So, if I have my function, and I'm going to draw it again, if I have my function and I'm calculating the gradient at a particular point, let's say I'm using that formula we just learnt to calculate the gradient at this point, what I'm actually doing is calculating the gradient of the tangent to the curve at this particular point. Now remember, a tangent is a line that only touches the point once. So I'm calculating the gradient of the line that only touches this point once, and we call that a tangent. We'll make that a bit bolder. We're calculating the gradient of the tangent to the line at point x. So for example, in a distance time graph, that would get us the exact speed at point x rather than calculating an average speed between 2 points. If you want to think of it as average speed cameras, well, it would make sense that the closer your average speed cameras got together, then the more accurately you're going to get what we call our instantaneous speed, or the speed at a particular exact time spot. So the formula we learn is what we call the fundamental theorem of calculus, which we usually call first principles. And it states that the limit as h approaches 0 of f of x plus h minus f of x on h, there's no equal sign here, importantly, our equal sign goes here, is equal to the gradient of the tangent to the curve, to curve f of x, y equals f of x, at point x. This is one of the most important things in the history of mathematics. It was developed in the 17th century by Isaac Newton, and it basically changed the world. So this is the fundamental theorem of calculus. Everything we do in extension maths from this point on will be using the fundamental theorem of calculus. Apart from one topic, everything we do will be involving calculus. So what we can do using the fundamental theorem of calculus, is calculate the differentiation of a function. So if I have a function y equals f of x, then the differentiation of f of x using the fundamental theorem of calculus, we express as y dash equals f of x, or y equals f dash of x, or dy on dx. Now, it's a bit funny with the pronunciations. We say dy dx. It's not dy dx, we say dy dx. Or df of x on dx. Df of x dx. It's a bit funny the way we say it, but it's just what's done. So the differentiation of a function of y equals f of x can be written as y dash of f of x, or y equals f dash of x, or dy dx, or df of x dx. So let's have a go at differentiating part 1, y equals x squared. So step number 1 is to, first of all, find f of x. That's equal to x squared. We also need to find f of x plus h. And that's going to equal x plus h squared, which is x squared plus 2xh plus h squared. Now to differentiate, we use the fundamental theorem of calculus, which states the limit as h goes towards 0 of f of x plus h minus f of x on h. We're using this identity and we're going to substitute in, and that's equal to m, my gradient. So, substituting into that formula, we have to write the limit every single line. Limit as h goes towards 0. If you don't write limit, if you just start doing this, it's incorrect. It doesn't make any sense. You have to write limit. F of x plus h is x squared plus 2xh plus h squared minus f of x, which is x squared, all over h. Now I know it's annoying, but on your next line you must write the limit as h goes towards 0. We can simplify this, my x squareds cancel. So I have the limit as h goes towards 0 is 2xh plus h squared on h. Now, the idea of the limit is seeing what happens when h is 0, or when h is infinitely small. So what we're going to do is substitute in 0 for h. So we can now put an equal sign and substitute in 0 for h. But that's a problem there. We've just divided by 0. So when we differentiate, we must always find a way to cancel h from the bottom denominator. So that is not correct. So before we substitute h equals 0, we must find a way to cancel h from the denominator first. So the limit, making sure we're writing limit each line, the limit as h goes towards 0, we know if we cancel this, this and this, that can be done, is going to equal 2x plus h. Now tick, we've cancelled h from the denominator, we can substitute in h equals 0. So this is going to be 2x plus 0, or 2x. So we've just discovered that if I have the function y equals x squared, y dash, or our differentiation, is 2x. This is what we call my gradient function, or the differentiation of y equals x squared, or dy dx equals 2x. All of those are correct ways of expressing that, or obviously y dash equals 2x, or f dash of x equals 2x. What does that mean though? If I were to graph y equals x squared on a Cartesian plane, y equals x squared, and we've just found that the differentiation of y equals x squared, dy dx, is 2x. So what this is telling us is that this is a curved line. Now we should know that we can't calculate the gradient of a curved line. It's not possible. But we can calculate the gradient of a straight line. Now you would have expected, maybe, that the differentiation of x squared would have been a number. It would have been a whole number because a gradient is a whole number. But we've actually gotten a function. Now that's because it's what we call the gradient function. So we have just found an equation that describes the gradient of every point at any point. So, for example, the gradient of the tangent to the curve, which is this, at x equals, say, 3. X equals 3. The gradient of the tangent to the curve m is 2 times by 3, which is 6. So the gradient of the tangent to the curve at x equals 3 is 6. The gradient of the tangent to the curve at x equals minus 5 is minus 10. 2 times minus 5 is minus 10. So dy dx, or the differentiation of x squared, is describing the gradient of the tangent to the curve at any point. Now what's special about that is that, let's say x squared was describing the motion of a particle moving around an atom, for example. Well, if we wanted to know the speed, if we had a distance time graph, if we wanted to know the speed, we could differentiate our function and we would be able to get the velocity. We know if we differentiate, we get a gradient. We know the gradient of a distance time graph if it's speed. So we can calculate its exact speed. Okay, let's do one more differentiation. So we're going to differentiate let's differentiate y equals x cubed. So, first up we go f of x is equal to x cubed. F of x plus h is equal to x plus h cubed, which is equal to x cubed plus 3x squared h plus 3x h squared plus h cubed. Substituting into our fundamental theorem of calculus, which is the limit, as h goes towards 0, of f of x plus h minus f of x over h. So the limit, as h goes towards 0, of f of x plus h is x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed minus f of x on h. These will cancel, and we're left with the limit, as h goes towards 0, of 3x squared h plus 3x h squared plus h cubed on h. We can cancel the h. Remember, we must cancel the h off the bottom. We're going to have the limit, as h goes towards 0, of 3x squared plus 3xh plus h squared. Now we've cancelled h on the bottom, so we can substitute in h to be 0, and we're left with 3x squared. So if I have the function y equals x cubed, dy dx, or its differentiation, is 3x squared. Now, importantly, the reason I'm recording this video is because we're about to recognize an identity. We notice that if I had y equals x squared, our differentiation dy dx is equal to 2x. I'm going to put a power of 1 here, and you'll see why in a second. We know if I had y equals x cubed, we've just discovered that dy dx was 3x squared. Now, there are many, many ways of differentiating. The fundamental theorem of calculus was the first thing that was developed, and then from that there were various rules that were the result of the fundamental theorem of calculus. So, if I differentiate dy dx, if I differentiate y equals ax to the power of n, I get a times by n times by x to the power of n minus 1. Which also means if I have y equals x to the power of n, if I differentiate that, I get n x to the power of n minus 1. If you differentiate using first principles, I imagine you'll do the proof in advanced. You will get this. This is what we call the power rule. So the power rule basically says that if I have x to the power of something, if I have the 2, I move the 2 down to here and subtract 1 from the power. So here you can see the 2 has moved down to here and we've subtracted 1 from the power. That's all that's happening. Down here, the 3 is moving down here. You can see it's moved down here. We've subtracted 1 from the power. So, rather than using the fundamental theorem of calculus, we're just going to use our power rule. Now, unfortunately, you'll have to know how to do both questions in the HSC definitely can say use first principles, which would mean you would have to do it the long way. But let's use the power rule to differentiate y is equal to x to the power of 5. Also, dy dx, we bring down the 5, and we subtract 1 from the power, 5x to the power of 4. If you did that whole long f of x plus h minus f of x on h limit process, you would get that as your answer. Question number 2, differentiate y is equal to x to the power of 10. Again, dy dx is equal to 10x to the power of 9. We bring down the 10 and we subtract 1 from the power. Question number 3, y is equal to 5x squared. Again, we bring down the power, 5 times by 2, x to the power of 1, which is 10x to the power of 1. So whenever you have a coefficient of x, you just bring down the power, times it by the coefficient, and subtract 1 from the power. Question number 4, y is equal to x cubed plus x squared. This one, we can basically split it up into 2 questions. Dy dx, we just treat it individually. This is another one of the results of the fundamental theorem of calculus. We can just differentiate these individually. So here we have 3x squared, subtract 1 from the power, plus 2x. Question number 5. Y is equal to 6x to the power of 5 plus 2x cubed plus 3x squared. Dy dx, we bring down the power, 6 times 5 is 30, x to the power of 4 minus 1 is 4, 5 minus 1 is 4, plus 2 times 3 is 6, x to the power of 2, plus 3 times 2 is also 6, x to the power of 1. Number 6, y equals x. Well, we know that this is to the power of 1. So dy dx, we bring down the power of 1, it's going to be 1x to the power of 0, which is 1. So if we differentiate a straight line, we usually just get 1. And that makes sense. The gradient of the line y equals x is 1. Question number 7, differentiate y is equal to 2x. Bring down the power, 2, x to the power of 0, which is 2. Number 8, differentiate y equals x to the power of 3, 2x to the power of 3 plus 5x squared plus 6x. So it's going to be y is equal to 2 times 3 is 6x squared, plus 5 times 2 is 10, subtract 1, 10x, plus, when we differentiate an x, it just really goes away, plus 6. Okay, last 2. If you differentiate a whole number, say y equals 2, you always get 0. Sorry, I forgot the dy dx. If you differentiate a whole number, you get 0. So last one, question number 10. Y equals 5x squared plus 6x cubed plus 2x plus 5. Well, dy dx is going to equal 5 times 2 is 10x plus 6 times 3 is 18x squared plus 2, and the 5 goes away. Okay. You will learn all of that in advance, and we will do more and more of that in extension, even more difficult. You will learn many, many other rules, such as the chain rule and the quotient rule and the reverse chain rule. But for now, we need to know this before you learn it in advance, because there's a polynomials topic on differentiation. Okay, hope that makes sense.